class, it's Mr. Hofstad here with the first lesson out of Unit 4, which is all about energy. Energy is quite closely related to dynamics, the unit we just figured out. And we also dove into it already in Science 10, so if you look back at your notes from that course or remember anything about it, well, this unit has a little bit more review than some of our coming up units, which is should be nice. So start with our nice cartoon. Here we got Sir Isaac Newton being approached by one of the Royal Academy members looking to make some money off of Newton. The classic idea of Newton coming up with the idea of gravity and gravitational potential energy from an apple falling on his head, and this guy just trying to take advantage of Newton in that way. Haha, great joke. So we have our first lesson all about work. And if you don't remember from Science 10, work is equal to the force times the distance. And we're throwing in this new cosine function. So work is equal to force times distance times the cosine of the angle between the force and the distance. So getting a little bit more complicated here. Let's look at work in a non-mathematic way, right? Just explaining what work really is. Work is done when a force moves an object or resists that motion. So when it moves an object, that's considered our positive work, and when it resists, we're considering that to be negative work. So, but it's all about forces over distance. That's our main takeaway from this here. Right, and in this diagram you can see we have a force, we have an object moving some distance, and the angle between the force and the distance, right, measured from our displacement vector up. And we'll find out quickly where this angle comes from and why it's important. Just like energy, work is measured in joules. Work or energy is the ability to do work. So they're kind of two sides of the same coin, but keep in mind that when we're talking about work, we're talking about joules, which would be newtons times meters. And you could break up newtons into mass times acceleration, and we can get all of the SI most basic units right from this idea of a joule. Force times distance, force is mass times acceleration. All right, we'll get to that in some examples later, I'm sure. So work is a scalar. This is really important, meaning it has no direction. Even though we can have a positive force or a resisting force lending itself to positive work and negative work, we don't really assign direction to work, so it's a scalar. It's kind of a weird exception though, because it can be positive or negative. But we still don't say we have work to the east. That doesn't make sense. We just have, we're doing work, right? It doesn't matter what direction we're doing it in. The only thing that matters is whether we are assisting the motion or, right, so positive would be assisting and negative would be resisting. Okay, so here's where we're kind of explaining the angle in our special cases, this ever important and kind of weird angle between our force and our displacement. So when force is in the same direction, right, and parallel to our displacement, right, this is our grade 10 version, easiest, simplest version of work. It's just going to be the force that's being applied to our object, right, this guy here, times the displacement, right, how far this box is being moved, right. And important to note that this is positive since it's helping or assisting the motion. All right, our next easiest case, we have force in the opposite direction. Now we have negative force times distance. All right, classic example would be friction. So it'll be a negative work since it's resisting. Right, still parallel to the displacement. Right, we have no angle, so we don't have to worry about this cosine function, right, because cosine of 0 is just equal to 1, right, or 180, however you're going to look at that. Finally, if the force is perpendicular to the displacement, we have no work. So that normal force is doing no work on this object because it's not moving a distance in that dimension, in that vertical plane. Right, so we're still kind of keeping in mind our two-dimensional vectors for this unit. Right, so since this is perpendicular to displacement, there's zero work being done by this force. No work. Since the force neither helps or resists the motion. Right, it's irrelevant to this displacement. It wouldn't affect it if it were there or not. It's not doing any work. So from this idea of perpendicular forces resulting in zero work, we can come up with this idea that you need to be parallel, right? If perpendicular is 0 and parallel is the full amount, only the component of the force that is parallel. So that's really important. We're looking for parallel components to determine the work. So if the force is parallel to the displacement, it's doing work. If it's perpendicular, it's not doing work. And we can always break up our 2D vector of force into its parallel component and its perpendicular. Right, here's our parallel and our perpendicular. Just our nice math symbols for those. So perpendicular does no work. All right. So there's two methods to determine the net work, kind of similar to how we determine net force, but now we're taking it one step further and multiplying that net force by that distance or displacement. So a net force is equal to our net work is equal to net force times the cosine of the angle. So essentially what's happening in this part of it is we're finding the parallel component. I'm pretty terrible at writing with my trackpad, as you can see. Here, I'll write it out for you. I'm also bad at spelling. Okay, so we have this parallel component coming from the net force times the cosine of the angle, because obviously only the component of the force that's parallel to this displacement is going to do any work, right? So once we find the parallel component, we can simply multiply it by our distance and we get the net work. Another way to do it is to find each of the forces and the works that they're doing, right? So this will make more sense during an example, but if we find the work done by each of these forces, right? So that would be F1, F2, F3, add together the amount of work of each of those, and you'll get this net work as well. So we'll do an example with both of those together. So if we have this block moving right at a constant velocity, okay, so there's a couple key things here. We know that we're moving to the right and it's constant velocity, which means our acceleration is 0. But we have a constant velocity we have a time. So I'm going to move on to my whiteboard so you don't have to struggle with this online trackpad nonsense. So we have our box with our force, our F1 and our F2, and zero acceleration. So constant motion, which of our formulas from our formula sheet back to kinematics are we able to use? Only these guys, right? V is d over t. They give us a velocity and a time. And look, in order to find work, we need our distance. Okay, so we're going to use our kinematic equations to find that distance. So they give us a velocity of 6.2 and a time of 8.9. Solve for distance from that. So multiply by t. Distance is velocity times time. Velocity is, I'm doing the order wrong, 8.90 seconds is the time, and our velocity is 6.2 meters per second, giving us a distance traveled of 55.18 meters to the right. Not that our direction matters because we're looking for work, and work is scalar. So we're looking for the work done by F1 first, F2 second on this 44 kilogram box. Okay, so we're going to start by looking at force 1, breaking it into this parallel component, right? So F1x, this is our parallel. So we're not concerned about this vertical component. That one is perpendicular. It's not going to do any work on our box. And we're trying to determine the work done. So that would be our 0. And they give us an angle of 25 degrees. I'll kind of expand this F1 down here. So F1, they give us as 710 newtons. We have to find this component using this angle. So this will be our adjacent, this will be our hypotenuse. This is what we're looking for, the x component of force 1. So using the cosine function, k, adjacent over hypotenuse, of 25 degrees, we get adjacent, F1x, over hypotenuse, which was 710 newtons. Multiply our denominator to solve for F1x, and it'll come out as 710 cosine 25. Sorry, I didn't calculate this one yet. 710 cos 25. 643.47 some change. I'll store that one in my calculator as A. Next step, we're trying to find the work done by force 1, call it work 1. It's equal to F1 x, right, our parallel component, times our displacement, and it's going to be negative, right? Negative since it's opposite displacement. Right, if we look at our diagram, we're moving to the right, right? So we're going to have this displacement 55 meters to the right. Since this force 1 is acting to the left, right? It's opposite to our displacement. We are going to end up with negative work, right? It's resisting this motion. Okay, throw in our numbers. We're going to get negative and then 643 times our 55.18 meters. It'll give us negative 35,507 joules. Very big, very negative. And we can put that into scientific notation or change our units from joules to kilojoules, which will divide it by 1,000, 3 decimal places over, 35.5 kilojoules resisting our motion. Okay, that was A. Now let's try out B, where we're looking for the F2's work. So we're going to be going the same distance. And this is where we can use a couple different methods. So we don't know the value for F2, right? We weren't given it like we were for F1, but we do know that we have uniform motion, 0 acceleration. So we'll use our principle of physics, 0, Newton's first law. F net is equal to 0, where the net force is going to be our F2 off to the right, our positive one, minus our x component, right? Because that is the component of force 1 that is in the same direction as our F2. All right, so we have this simplifying to f of 2 is equal to f1x is equal to, we calculated it before, as 643.48, blah, blah, blah. I have it still stored as A in my calculator, newtons. And now we're going to the right rather than left. Okay, now we have our force, we have our distance, easy peasy. Work done by 2 is equal to F2d cosine theta. This is nice and easy. That equals 1 because we're parallel. Is equal positive because we're in the same direction. F2 and our displacement. Right? Positive force in same direction. Right? Same direction is positive, opposite direction of the motion, we got negative. As our displacement, as our motion. Throw in our numbers, we get 643.48, 55.18 meters, and it'll come out at positive 35.5 kilojoules. We already calculated that last time. Nice and easy calculations. Right, and our other method for that would just be to understand that since our net force is 0, the work done by the net force is also 0. Right? Net force has to be 0 because our acceleration is 0. So method 2. We have acceleration equals 0, F net equals 0. Net work is 0. So work 1 plus work 2 is 0. So we know that the work done by force 2 needs to be opposite and equal to work done by 1, right? And we had negative 35.5 kilojoules for work 1, so work 2 has to be positive 35.5 kilojoules. Okay, so that's a way to solve that question as well. Okay, let's take a look at our next example. We have a box that weighs 17 kilograms. It's being pulled with this unknown force F, but due to the friction, which is 120 newtons in the opposite direction, obviously friction always needs to be resisting our motion. This is actually greater than this force applied. Think about almost tires on a car screeching to a halt, right? The force of friction is greater than that forward force of the momentum of the car. Something similar here. Our box is sliding on a sticky surface, right? And the force that's pulling it, whether that's with a string or somebody pushing it, whatever it is not enough to overcome the friction. So it's going to start traveling to the right, and it's eventually going to come to rest. And we know it will be accelerating at 1.85 meters per second squared. So they give us a bunch of information about its speed. Actually, they only give us information about speed. They give us initial speed, acceleration, final speed. We're working with finding work here, working with work. So let's look at our kinematics. So here we're working with uniform acceleration. So instead of only using, well, it's pretty dark. You can't really see it from there, but instead of using those formulas for uniform motion, we're now able to choose from our 5 other equations for uniform acceleration. And we're going to choose that based on what we don't know and don't care about in the question. So they give us acceleration. I'm going to say my reference system is positive to the right, negative to the left. So I've got a negative 1.85 meters per second squared acceleration. I have an initial velocity given to me to the right. It doesn't say that it's to the right, but if we're starting with some speed at all and we're going to rest, we know that our starting velocity needs to be opposite to the acceleration. That's the only way we can slow down, when our speed and acceleration are opposed to each other. So it's moving at 9 meters per second to the right, positive 9.00 meters per second. We want to find, sorry, that's supposed to be final velocity. It's saying it comes to rest, 0 meters per second. And we want to determine our displacement or distance to use to find work. We need a force and a distance. So obviously we're going to look at this distance. So time is our useless little piece here. Not useless actually, because it's going to tell us to choose the equation that doesn't have time tied to it, which is of course our last one. VF squared equals VI squared plus 2AD. So from all of this, I've got VF squared is equal to VI squared plus 2AD, where I'm looking for displacement. Displacement is VF squared minus VI squared. This will be a 0 divided by 2A. So negative VI squared, which was 9, divided by 2 times our acceleration of negative 1.85. And we are working with a displacement of 21.89 meters. Okay, so we have displacement. Now we need to find our force. The order of that doesn't really matter. They're not tied to each other than in our final equation. So looking at our applied force and our friction force and our acceleration, we know that we have Newton's second law, unbalanced forces, where F net is equal to mass times acceleration. We're given a mass, we're given an acceleration. We know we're looking for this force. F net is this force minus our force of friction. So this force is equal to our mass, 17 kilograms, our acceleration, negative 1.85. And we're going to add to it our force of friction of 120 newtons. So that unknown force here, where it's applied, is going to be equal to 88.55 newtons. And it's positive. So that's our force pulling the box to the right. Now we're trying to find, well, the question is, we want to determine the work done by this F in the time that it takes to bring it to rest over this displacement. So the work done by F is equal to our force F times our displacement times the cosine of the angle between them, which in this case is 90 or 0 degrees, right? They're parallel. So whenever we're working with parallel forces, right, we can remove our cosine of theta. And we get positive because it's in the same direction as our displacement. Right, this force F is in the same direction as this displacement. Even though we're accelerating to the left, we're still moving to the right throughout that motion until we finally come to rest. So this will be equal to positive 88.55 newtons times our 21.89 meters, and we get the work done by this force is equal to 1938.53 joules. Again, we can convert this into scientific notation or kilojoules. I'll do it different than I did last time. I'll convert it to scientific notation. (1.94 times 10 to the 3 joules, or kilojoules. That's essentially what that means. Okay, one last question for this lesson. I'll do this guy on the screen here because it's a lot easier than me drawing it by hand. So throw back to our kinematics and finding area under graphs, right? When we had a displacement time graph or a velocity time graph, we could find the area. So yeah, it was using the area under a velocity time graph, which would give us displacement, because displacement is velocity times time. What is force times displacement or distance? That's going to give us work, right? Work is equal to force times distance, which in this case, force is our y-axis and displacement is our x-axis. So if we're trying to determine the work, we need to find the total area under this line. Total area between line and x-axis. Okay, so what that looks like, we're looking for the area underneath this line all the way to our x-axis. Kind of tricky to find the area with one step here, so instead we're going to break it into two shapes. We've got a triangle above and a rectangle below. All right, so we'll call this one area 2, A2, and our triangle will be area 1. Okay, so our area 1 plus our area 2 will give us the total area of both the triangle and the rectangle. Let me try to move this. Okay, so for our triangle, we're going to do half of base times height, or length times width, however you want to talk about it. So sorry about this. We've got half of our base, which was 9 centimeters, times our height, which is from 2 up to 6.5. So that's going to be 4.5 times 10 to the 3 newtons. Right, pay attention to our units there. Forces in times 10 to the 3 newtons, or kilonewtons. And we need to add our rectangle area. Base again is 9 centimeters, and our height is 2 kilonewtons. So the total work done here, when we add that together, we'll have to convert this to meters. 0.09, 0.09 meters from 9 centimeters. So meters times newtons, I guess we'll have to keep that as 2,000. And 4 times 10 to the 3, right? We need to keep our units consistent. Meters and newtons are our standard units. So if we're calculating work in joules, we need to have meters and newtons as well. And this will give us 382.5 joules. And we need significant digits, 383 joules. I don't know why this is looking like that. There, sure. Working with what I got, doing my best. So the area under a force distance diagram will be work, because area is base times height, right? And if we look at the units, that's going to be meters times newtons, which come out as the units of work, force times distance, and Newton meters are also joules. So units are all important in physics. Pay attention to them. They are a real lifesaver. All right, thanks for going through lesson 1 on work with me. I will see you over on lesson 2.